Volume up? Okay. There's been, it's really loud for me because I'm right here. Yeah. There's been a fair amount of talk about putting UTXO commitments in BitTorrent blocks. Whether this is a good idea or not, I don't know, but on the off chance that it might be a good idea, I spent a fair amount of time making an actually good Merkle Set Implementation, which is what you need to put UTXO commitments in Bitcoin blocks. This has all their benefit that there's actually 1,000,001 uses for Merkle sets in general, and it's actually an interesting problem-making one that performs well, so I figured, hey, might as well make it, and if it's not useful for this, it'll be useful for someone. Okay, so Merkle set, for those of you who aren't aware, this is sometimes people not in the know call it a hash set, or based on hash tree, and Ralph Merkle gets really mad at you. So since he's still alive, we still call them Merkle trees. A Merkle set is a set which contains arrays of bytes, and it keeps track of its Merkle root. So it's like that. So all these things at the terminals here are things that are contained in the set, and these things in the middle are summaries, and here's the root. And you can use the root to prove, for someone who has the root, whether something is or is not in the set. So there's a series of interesting engineering problems to make these really perform well. First question is, what hash function should we use? The obvious choice is SHA-256, because it's the standard. And the really big benefit of SHA-256 is that it's the only thing that really has hardware acceleration. And it's the only thing that's going to have widespread hardware acceleration for the foreseeable future. Unfortunately, SHA-56 isn't super fast in software, and on top of not being super fast in software, it has just funky padding issues. So if you just concatenate two hashes, it doesn't line up nicely and has a whole other block that needs to compute on. So it turns out the best thing to use is Blake 2s, because everything here has 256-bit outputs, and Blake 2s's block size is 512 bits. There's this slightly frustrating thing with the flavors of Blake, that there's Blake 2s, which is optimized for 32-bit systems, and there's Blake 2b, that's optimized for 64-bit systems. So the obvious choice, since nothing in the world's actually a 32-bit system, would be to use Blake 2b. Unfortunately, Blake 2b has a 1024-bit block size, so it's actually slower. Yeah, I know. I bugged them, the authors of Blake, about whether it would be possible for them to do a new variant, and they're like, that would be a lot of work. So this is where we are today. On top of that, it turns out you do sometimes want just a teeny little bit of metadata. Blake 2b is really good about when you give it exactly 512 bits. It doesn't need to do any padding. It processes exactly one block. But you do actually want some metadata, so it's a good idea, if you're going this route, to sacrifice 2 bits to metadata so you can encode information about what kind of a hash it is. And the values I'm using are terminal, meaning this is just a hash of a string that is being stored. Empty, meaning there's nothing here. Or intermediary, meaning this is a hash of multiple things below it. Or invalid, which basically means this hasn't been calculated yet when you're using lazy evaluation. That's really handy. Okay, so I'm using a Patricia Trie. There are a number of subtle, different ways of approaching making Merkle sets. The most straightforward one is basically you just sort everything and put it in a list and start adding it together. That can't be efficiently updated because the positions of everything aren't super canonical. So everyone who's spent time on this has wound up using a Patricia Trie, which basically positions everything based on what the bits in it are. So here's the root right here, and everything that has a 0 as its first bit that you're looking at goes here. Everything that has a 1 as its first bit goes here. You go down. Empty can turn up if everything is on the same side. So on this spot right here, everything starts with a 0 bit. So there's these two things here, both of which have 0 bits, but you include empty there and put that in explicitly. The reason to put in empty explicitly is so that you can have nice, clean proofs of non-inclusion. If you try and optimize out the empties, you can still have proofs of non-inclusion, but it's really ugly. So there's one more trick that's actually part of the semantics of this that I came up with, which is that if you only have two things below a particular point and it's empty on the other side, you do a pass-through. So if we look down at the bottom here, we have two terminals. And so the thing that has those two terminals as children has to do a calculation to find out what the root value is there. Above that, there's something where everything on the other side is empty. So that does a pass-through, because it only has the two values. And then if there's another layer that's also empty on the other side, again, does a pass-through. Now up here, because there's something on the other side, it has to calculate the two of them together to find the value here. And above that, even though it's an empty on the other side, because there's now more than two things below it, it needs to do a hash calculation again. This is worth doing because this gets rid of about half the hashing operations you need to do. So it's actually a pretty substantial optimization and worth doing. That's it for the actual optimizations that affect the semantics of how this works. So I actually have on my GitHub, it's called Merkle Set, an implementation of this. It's in Python, which is ridiculous. It needs to be ported to C. That should be done soon. And that has a reference implementation, which is very straightforward, and a highly performant implementation, which isn't highly performant because it's in Python, but it will be when it's ported to C. There's interesting subtleties to what the performance needs are here. On modern architectures, you wind up spending all your time waiting for memory. And the exact subtleties of how that works aren't clear. But the basic idea is when you're accessing memory, you want to get things that are near each other all together. So in the extreme version is like a physical hard drive, where a seek is very expensive, but reading in a whole bunch of macro stuff at once is not. SSDs less so, but this continues up the whole memory hierarchy. So it's a question of how do you arrange things in memory so that things that are related are near each other, parents, children, siblings, those kinds of things. So I came up with this concept of, well, the vernacular I use is a block. I didn't invent the concept of memory management, but everything that's allocated via single memory allocation I'm calling a block. When I first started working on this, it didn't play nice with regular memory allocators and wanted some gigantic allocation done up front, but I figured out how to make it actually act normally after a number of complete rewrites. The sizes of blocks aren't obvious. There's really bad documentation everywhere about how long things wait for and how near things need to be to each other to get better read times and how much of an improvement those are. So I made that parameterizable in my implementation, and that needs to be optimized for the local CPU, memory, bus architecture, and the phase of the moon. That's the high-level view of what this is going to do. So there are these two kinds of blocks. There's branch blocks and leaf blocks. The root is a branch block. Every block can have many children, but only one parent. That makes things behave a lot better. No sibling relationships between them of any kind. Every time there's an overflow from a parent, it goes into one of the children. It's possible for multiple outputs of a parent to go into the same child if the child is a leaf block. So I'll get to the layouts of these in the next slide, but the basic idea is usually the terminals are leaves and everything above them is branches. And this way I've scrolled this out here is actually fairly realistic in that it's pretty normal for a branch block to only have one or a few leaves below it, where branches tend to fan out very, very fast. When you're doing a memory lookup, it tends to go branch, branch, leaf. So these are the formats that these are. A branch block has a reference. All the things that are of size 8 here are memory pointers. A branch block has a a pointer to its active child, which is a leaf block, and it has a Patricia of depth. The branch has depth as a parameter to how it works. Its size is roughly 2 to the power of the depth. Each Patricia thing contains the left hash, meaning the hash of everything starting with a 0 bit below the current position, followed by the right hash, the root of everything starting with a 1 bit below the current position, followed by the 2 child things, the Patricia of the zeros, size n minus 1, and the Patricia of the ones of size n minus 1. So this is a recursive data structure here. Actually, this one trick of just putting the left and right next to each other should really, really improve lookup times a lot, especially when you're updating things, because when you're recalculating hashes, you want the siblings all the way up, and they're right there. When you finally get down to Patricia of 0, there is a pointer to one of the children and a position within that child. Children have positions within them, indices within them in leaf blocks. If the child is a branch block, position is just set to FFFF, which is an invalid value. So branch blocks are balanced by their nature. Things don't move around within them, they're set positions. The biggest subtlety here has to do with this active child. What happens is the branch block will sometimes have overflows within itself, where there's 2 things that need to go to the same out position. And sometimes leaf blocks will overflow as well. A leaf will get full. When that happens, it needs to decide where to put the overflow. It puts it in the active child. This does a pretty good job of memory allocation. So when you need to, you go and make a new active child, and that starts with nothing in it, and you start filling it up until it's full, and then you make another active child. So usually, all the active children are basically full, and except for one, which has the overflow, which is as full as it needs to be, and you only do a new memory allocation when you really need to. So this does a pretty good job of not pre-allocating a lot more than it needs. So within leaf blocks, this is an interesting subtlety. A leaf block is basically a list of nodes. It has first unused, which is a position within itself. Everything here that is 2 bytes is a position. And num inputs, which is the number of times the parent has inputs going into it. And then just a list of nodes. So nodes can be either full or empty. A full node it looks an awful lot like one of these Patricias. It has the hash of everything on the left side, hash of everything on the right side, and then it has the position of the child node on the left and the position of the child node on the right. When I say left, I mean a low order 0 bit. And right is high order 1 bit. The empty node, this is kind of interesting, has a next pointer and then just zeros. The reason for this first unused and empty node here is the unused nodes form a linked list. So when you want to allocate a new node, you just pick the next one and update first unused to point to the next one after it. And if you hit the last one of them, you go, oh, I need to do an overflow, and you copy out into the into the active child, unless the active child is full, or you are the active child, in which case you make a new active child, or maybe you only have one input yourself, in which case you don't copy out into the active child. You actually take your whole block that you are and copy it into a new branch block, which likely has a new leaf block underneath it. There's a lot of really crazy recursive stuff here in the code, which is a little bit subtle, but looks simple. And I just covered everything there. Okay, that's all of that. I have another interesting thing to talk about, but first I'd like to answer any questions people might have. Yes?
Why do you not use the skip hash mechanism when there are more than 2 leaves below it?
What do you mean by the skip hash? Why don't I skip when there's more than 2 below? That's because if you want to have a proof of non-inclusion, you terminate at an empty. When there's only two things below, you just give both of them. And so it's not a big bloat on the size of your proof. That's why that's special case.
The difference between a Merkle tree and a Merkle Trie, T-R-I-E?
I'm not really sure the difference between trees and tries. I'm stating a thing that implicitly explains. I'm not really sure of the real difference between the meanings of trees and tries. I think try has an I in it and tree does not. Patricia tries are called tries, and generally if you take a more straightforward approach of just cram everything together by position, that's usually called a tree, and it's not easily updatable, but I could be wrong on that one.
Try comes from retrieve, and it's a tree in which search is easy, which is where the concept of you're splitting based on the key value rather than based on balancing.
Okay, so
But every try is a tree.
yeah, so Peter just explained that try is from the term retrieve, and it basically implies that everything is balanced so you can retrieve quickly. So anything even vaguely resembling what I'm talking about here, even without having efficient updating, would be a try. Yes.
So really simple question. There's like 1 million Merkle tree libraries in the world. Why did you make this?
As far as I'm aware, the ones that are out there right now don't actually do a good job of getting good cache coherence. That doesn't seem to be a thing that they worry about. Having to worry about cache coherence is sort of a relatively new thing in computer science, having to do with computers being weird and fast these days, and like so fast that things moving around the bus are actually a problem. Like the fact that, like really what it amounts to is a die is this two-dimensional thing that needs to get like data around on these highways going over it, and the size of the die is like quadratic, and the width of the highway is linear. And now that we have these like megalopolises on chips, like this is actually problematic. So there aren't too many things that actually talk about this kind of optimization. And like more recent versions of Introduction to Algorithms talk about like sorting algorithms that will work optimally regardless of how your cache coherence properties work and things like that. But it's not something that people usually worry about too much. So I decided to try and make this as performant as I possibly could, because that was a really interesting problem to work on.
Can you talk about that just for a second? Like, when you say performant, do you mean it more gracefully handles larger trees, or what are some of the performance characteristics?
The relevant performance characteristics have to do with, well, there's a few different kinds of operations it can do. It can check for inclusion, and it can update. And when it's doing updating, there's different usage patterns of it updating. So maybe it has a lot of retrieves interspersed with updates, and maybe it has like whole batches of updates followed by retrieves. And when you're doing retrievals, maybe you care about proofs and maybe you don't. My thesis here is that if you don't care about proofs, you should be using an ordinary set, because a hash set has very, very good memory cache coherence properties, because it knows basically exactly where it needs to look at every time someone tries to retrieve something, where any kind of traversing a tree is going to be very slow by comparison. So if you want to do lots of checking for inclusion and don't care about the proofs, you should just have two separate sets, one of them a Merkle set, one of them a regular set. The most relevant thing here, as I was thinking about this, is like how long would it take you to go over all of the blockchain history? So that for that particular use case, what you're doing is for each block, you're doing a whole bunch of updates followed by getting the root. And then you're doing a validation of doing a bunch of retrieves for the next block to check that everything is in there. So that's kind of a specific usage pattern. You could write something to specifically try that. That has a fair amount of lazy evaluation that can help because you have these big batches of updates in it. And there's this interesting subtlety that when you're doing big batches of updates, you should sort them before going ahead and doing the, you should sort them before going ahead and doing the updates. And actually the way I'm obliterating the 2 high order bits here isn't super friendly with that because you actually want to sort starting with the 3rd bit instead of the very 1st bit. But I haven't yet put in a convenience function saying, here's a whole bunch of updates to do at once, and do them kind of in the right order because that's a weird gotcha for people to have to know to do. But yeah, there's a bunch of different patterns, and because it's so hard to actually get even sane information about exactly where things bottleneck because of memory stuff, I just tried optimizing everything I could. There weren't too many weird trade-offs to make, so I just used all the stops. Yes?
So I don't know if you've looked into it, but as I recall, Blake 2 has this personalization functionality, and you looked into using that instead of robbing bits for your.
I'm not familiar with that.
Okay, so the way it works is that basically the initial state of the Blake 2 hash, you can set to different values based on running Blake 2 to pre-initialize it. And so you can use this to separate the domain of separate hashes.
Oh, yeah, that would probably be a much more elegant way of, that sounds like a much more elegant way of adding the necessary metadata than losing the 2 bits of security
Yeah,
and
you just
sacrificing
re-compute
it.
it and just keep it around.
It really is necessary to do something along those lines because otherwise someone might try and store a tree root value in the set, and you can't tell whether it's an internal or an external value. So
I think the personalization is important.
yeah, that sounds like a better way of doing it. That isn't, the APIs that are made available in the default implementations of these tend to not give you all those fancy bells and whistles. So I was unaware of that being there as a feature.
You were talking about the anomalies of the real world. I was wondering what kind of tests have you done?
Well, because my implementation so far is in Python and needs to be ported to C, I should mention that it's really weird-looking Python that's meant to be ported to C specifically. So there are these data structures that have pointers in them. You can't actually do that in Python. It doesn't like taking just a random bunch of bytes and treating it as a pointer to some Python object. So I actually took all the memory data structures and put them in a hash table, and there's ref and deref methods for getting stuff into and out of the hash table. Yeah, that's kind of weird. It actually is quite handy having everything in there because as part of debugging the whole thing, I wrote audit methods, and the audit methods actually do go over everything in the whole hash table and make sure that there's nothing that's been orphaned and forgotten about, which wasn't deallocated when it should have been. I did read over data about how hard drives work and SSD drives work. And so SSD typically has a defined page size that's like 2 kilobytes, and you probably want to align with those when you're doing those. And hard drives, things should be pretty big, on the order of like a megabyte for the blocks if you're having to access it a lot. And you get into those regimes, you get things where you really only want like the terminal leaves to be on the disk because they're kind of big, and you want everything above that to actually be in memory, and you basically spend all your time waiting on the disk. When it gets to more fine-grained things about okay, if I'm storing this entire thing in memory, not on an SSD drive, not on a physical hard drive, it's all in memory, how big should my branch and leaf blocks be? The available documentation is ridiculously bad. The indications are that seemingly similar machines have just radically different behaviors. There's a library called fastest Fourier transform in the West, and what that thing does is the first time you run it, it just benchmarks itself on the current machine and decides what its magic number should be. I think that might be the best approach to these kind of weirdo problems.
So your block structure doesn't change the resulting root hash? So you can
Yeah. The block structure absolutely does not change the root hash whatsoever. I actually implemented this as a very simple reference implementation, which is quite straightforward. And it has some nice properties that, like, if you're doing lots of things with lots of rollbacks and stuff and you want to keep many roots without copying everything over, that's pretty handy because it does, everything is immutable in it. Where the performant one, everything is very mutable, and if you want to get back, you have to roll back. Yeah, but they do absolutely the exact same thing, and I have these very extensive tests where actually the way the tests work is they have just a random bunch of strings, and they repeatedly add one string at a time, and it records the root every single time and makes sure that everything that has been added is still there, and everything that hasn't been added isn't there yet. And then it deletes them one at a time, starting at the end and working its way back. And after it's done that for the reference implementation, it does that for a whole bunch of different sets of parameters, including fairly degenerate ones, for the performant implementation. I found a lot of bugs that way. It gets 98% code coverage with a rather small amount of test code, which is very nice. Any more questions? Something which I'm sure will be really controversial. Unfortunately, the Bitcoin devs mailing list has gotten completely drowned in discussions of subtleties of upgrade paths recently. So there hasn't been too much discussion of real engineering, much to my dismay. Using a Merkle set is kind of a blunt hammer. It's kind of like all problems can be solved with a Merkle set. And maybe in some cases, something that's a little bit more white box, that knows a little bit more about what's going on under the hood can perform better. And so here's a thought that I have. This isn't super fleshed out into a proposal. My Merkle set thing has an actual implementation with defined behavior. Right now, the way things work, you implicitly have a UTXO set. And when you have a wallet, it has a private key. And it wants to do something, so it generates a transaction and sends that to a full node, which has a UTXO set so that it can validate the transaction. And the size of the UTXO set is approximately the number of things in the UTXO set times 32. It's the number of bytes, roughly, that are being stored there. So there's this problem that this thing down here is kind of big, and you might want it to be smaller. There's been discussions of maybe you could use TXO Bitfields. I had a very collegial discussion with Peter Todd about his alternate approach to this whole thing, wherein I said this kind of weird comment, because he likes TXO Bitfields. I said that the thing that might actually be useful there is that you can compress things down more. And it turns out that that really actually helps a lot. So I have this idea, which is the TXO Bitfield. So UTXO is all the unspent transaction outputs. TXO includes all transaction outputs spent and unspent. So the idea with the TXO Bitfield is you have a wallet, and the wallet contains its private key and a proof of position. So the idea is as things are added to blocks, each one of them gets a position. And that position never changes. No matter how many things are added later, it's always in the same position. So the wallet then wants to make life easy for a full node when doing its validation. So the wallet takes its private key and makes a transaction, and then it takes the proof of position, which it remembers for the relevant inputs that it's using, for the relevant inputs that it's using, and bundles that with the transaction to send it to the full node. And the full node is then going to put it into a block to send to other full nodes. Or a miner's going to put it into a block to send to other full nodes. The proofs of position are going to be substantially larger than the transactions, so that's a trade-off that this incurs. So this goes to a full node, and the full node, it has to remember a little bit more than before. It has to remember a list of position roots per block. There are other trade-offs, but that's a reasonable trade-off to make. So For every single block, it remembers a root of a commitment that can be canonically calculated for that block of positions of all the inputs in it, which allows it to verify the proof of position. And it also has a TXO bit field. So the full node is going to take the proof of position and verify the alleged position on using the data it remembers for validating that. And then it looks it up in the TXO bit field. The TXO bit field is, in the simplest implementation, a completely trivial data structure. It's a bit field. And you just look up directly by position. So there's no complicated memory, anything here. You just right there. It's one lookup. It's probably very close to other lookups because you're probably looking at a lot of recent information, and it's even closer because you've compacted these down to 1 bit each, which make them much closer to each other. And it also is very small. The size of the TXO bit field, if you just implement it as a bit field, is equal to the TXO size divided by 8. So you see this is divided by 8, and this is times 32. So that's a constant factor of 256. Now, computer science people don't generally care that much about constant factors, but a constant factor of 256 actually really does make a very big difference in the real world. And this also has the benefit that, like, my Merkle set is a couple hundred lines of fairly technical code. It has extensive testing, but it's not something that I particularly trust someone else to go ahead and re-implement well from the spec. It's something where you fully expect everyone who uses it takes the existing code base and existing tests and ports them and gets those tests working again. Where this is something that I would have much more confidence that other people who go re-implement it from a spec are probably going to do it right. Now, the downsides to this are, one, that these proofs of position are much bigger than the transactions. And two, that you do this based on the TXO, this is based on the TXO set size rather than the UTXO set size, which probably is trending towards some constant that I'm not sure what it is, but you can imagine a scenario where in the long term that grows without bound. Now there is a pretty straightforward, well, there is a way of fixing that, which is you make a fancier bit field. When a bit field is sparse, then in principle, at the expense of it being much more interesting to implement it, you can maintain the exact same semantics while making it so that the physical size that the bit field is using is equal to the number of bits that are set to 1 times the log of the total number of bits, which is not scary in the slightest. That's not going to get above like 10, right? And this is still going to be quite small. Now, in order to get that work, you'd have to go through an exercise very much like the one that I did already for making a good Merkle set, which is someone who really knows what they're doing, has to spend a while thinking about it and experimenting with approaches to implementation to really, really get it to perform well, while a straightforward bit field is just trivial. Just do it. So this is an idea that I had. Any discussion of this got completely drowned out in this very important discussion about Segway. But I think this is an approach worth considering because with the given caveats of its performance, it has a lot going for it as compared to the blunt instrument of putting UTXO commitments in blocks in Bitcoin. Now, Merkle sets can do a lot more things for a lot more stuff than just in Bitcoin. I think they really shine when you have truly gigantic sets of data. So people who have like permissioned blockchains should probably really be the ones using Merkle sets, not so much Bitcoin, because it intentionally makes life easy on nodes and doesn't have a huge amount of traffic in it.
This, the proof of position, that position data, is that immutable?
Yes, position data is immutable. It only grows.
Okay, so that's the big distinction from Peter Todd's proposals, where he basically is fusing the bit field and the position data and takes out proof stuff.
Yeah, Peter Todd's idea with keeping the whole TXO, he likes indexing things by position on the grounds that the recent stuff is probably getting updated a lot. And And by organizing things kind of in memory that way, you get these like memory efficient lookups because it's all hitting the most recent stuff. Now this approach here gets that and more because you've compacted it down. So you're a lot more likely to hit things that are near because everything's fitting in a smaller area. And it still has this pattern that all the recent stuff is right there. So that is a benefit of the whole thing. I don't think that's anywhere near as much of a benefit as, first off, in this implementation, in the trivial Bitfield implementation, knowing exactly where the bit is, so it's just one lookup. And then the constant factor of 256 is a really, really big deal.
Yeah.
Along with it just being a really easy implementation to do, which I like.
Yeah, the real challenge with Peter Todd's proposals previously is that the wallet had to track basically the proof of position would change over time.
Right. Oh, right. Yeah. That was actually the thing that really inspired me to do this. Is I don't want wallets to have to keep track of everything. I don't want wallets to have to keep track of blocks. I want a wallet to be able to come back to life after years of being deactivated and still be able to make functional transactions. And by making it so that proofs of positions never change after like a few blocks, basically after you're past the reorg period, that keeps that property. So it makes wallets like really brain dead simple to write and to have function.
Yeah, makes sense.
I got through this talk very quickly. Does anyone have any more questions about this? Yes.
Can we wait for the mic?
Can you describe the proof of position, like what's actually in that, what information is contained in that, and how does it affect how Bitcoin blocks or transactions?
Yeah. So the proof of, so to make a proof of position, you have a canonical way of taking a block and calculating a position root to it. So we're not adding anything. One nice thing about this is that it doesn't involve adding anything to Bitcoin blocks. So you get a block, and you look at it and you say, okay, well, if I take the information about the order of everything in here and I put it in this sorted order of their position and I make a root for it, this is what it looks like. And it's a canonical calculation based on the blocks, which are defined by their hash. So me and everyone else will come up with the exact same root for this. So I calculate this once and then I actually forget everything but the root. I had it at one point, so I know it's valid, but I don't keep the whole thing. And so someone else who wants to prove position, right? So this proof of position, it starts with like, oh, well, everything up to this point had this number of things in it, and here's the list of things in order. So someone else who wants to make the proof of position, they include just the subset, the like path up that thing to the root that gives enough information that you can verify the offset of this one particular UTXO from what the value was at the beginning of this block. So no new things added to Bitcoin commitments, and it's just this canonical calculation that everyone can verify separately, and then the proofs of position will work for everyone.
Could I try to restate the benefits of this?
Sure.
Yeah, so the advantage of this sort of proposal is you currently with the full node today, to validate blocks, you need this UTXO set, which is maybe 2 gigabytes of data. And what Bram is proposing here is a scheme where the full node doesn't need to store that. Instead, it stores this Bitfield, which is a factor of 256 smaller, plus an additional hash per block. So that's a big improvement in savings for the minimum resource usage for a full node. The downside is that the transactions are much bigger. So instead of a transaction being 200 bytes, maybe it's like a kilobyte or something like that, because it has to carry along these proofs to basically remind the node of all the data it forgot. And there have been some proposals to do things like this for a while. Peter Todd has had a number, and most of those had some challenges where the wallet would have to sort of keep a passive view of the network in order to keep updating its proofs. And this proposal doesn't have that problem. So it's much easier to implement for the wallet and probably the node as well. So then there's this question of what's worse for people. A lot of storage on disk required to have this UTXO set, or a lot of bandwidth to have the transaction overhead. And there's a bunch of wrinkles in the discussion on this, including the fact that you can have a peer-to-peer level trade-off where you could have nodes that have the full set of data, and they didn't have to send it over the wire and things like that. And the other detail in this is that for M-scheme scales related to the TX output count, not the UTXO size. The TX out count is all history, not just the unspent size, so that's a lot larger. But because of this big savings, maybe it doesn't matter.
Yeah, and like I spent maybe too many words trying to explain. When the ratio between the size of the TXO set and the UTXO set, it becomes very large, you can start doing tricks where you compactify this bit field, and in the asymptotic, the size of this bit field will then be the UTXO size times the log of the ratio between the sizes between them, which is totally under control. But that's not trivial to implement. That doing that well is an exercise of the same kind of order as how much work I had to put into making a decent Merkle set, which is non-trivial.
But you don't have to do that.
It's totally not necessary right now. Today, this bit field is so small, it's not scaring the size.
So, just to clarify, right now, let's say you've got about 1,600 transactions per Bitcoin block on average right now? Something like that?
Inputs and outputs maybe, so 2,500 transactions. Per
Okay, so are we talking about adding so much more data that we're going to go down to a smaller number of transactions per block, or is this separate from that?
No, we're not proposing changing the number of transactions per block.
No,
I didn't think so, but I just wanted to make sure.
The way to think about this is what's just more expensive for users overall. Is space more expensive or is bandwidth more expensive? If bandwidth were free, then win, right? And if bandwidth's very expensive and disk space is very cheap, then this is less attractive. So there's a trade-off surface where this makes more or less sense.
Yeah, the idea here is we're trying to just make technical solutions that can keep up. We're trying to not actually, as much as possible, avoid doing anything that touches the semantics of Bitcoin at all, and just make it so we can pour some magic pixie dust on the problem and make the issues go away, and people can stop discussing hard forks to fix them.
Yeah, I just wanted to very briefly answer his question in a different way. Your blocks would be exactly the same size still, and your transactions would be the same size, and all the accounting over it would be the same thing. But when I give you a block or a transaction, in addition, I also give its proof that the outputs it's pending existed in the past. But that's just auxiliary information I pass along with the block, and perhaps you could even not request it and still keep the UTXO set. So it doesn't change the canonical block data, it just changes what I need to give to you in order to verify it.
That makes sense.
You could farm out the proof of position, right?
Yeah.
Your wallet wouldn't need to do that. You
Yeah,
You
the
just have to
wallet
service
can
it.
just be given the proof of position and remember it.
Yeah, that was the solution that Peter Todd's proposes, where this proof had to be constantly updated. His answer was to say, yeah, you'll farm that out to someone else, and you can easily pay them to do it. But in this case, there'd be no real reason to do it. You would just, the only reason you'd need a third party to give it to you is if you went offline immediately after getting paid. But if you were online when you got paid, you just save it and you're done. Because it never changes. You get it, it only changes under reorg, rather. But once your transaction is confirmed, you can just save that data. And if you do lose it somehow, then yeah, you go and ask for a third party. And you can even give the third party the transaction without the proofs and an extra output that would pay them, and then they would provide the proofs and get paid for providing it for you, because they made your transaction valid. Yeah.
Yeah, the proof, even if you've lost the proof of position, you only need to find one truly full node that can go look up the proof of position, and then you have it. And then that proof can be sent around to everybody else in the whole network thereafter.
Are these Bitfield, are the Bitfields stored per block, or are they sort of aggregated into?
It's one giant bit field for the whole history. And if you start looking at the very beginning of it, the very first bit is the very first UTXO of the Genesis block.
No. It's the block 1. Block 0 doesn't create an output.
Oh, okay.
It was never inserted in the database.
Well, since block 0 has 0 outputs, the very first output is block 1.
Yes.
And then there will be some number of bits for that, and then follows the block 2, 3, 4, and so on.
So each position is like an absolute position in the entire, okay.
Yeah, it's absolute positions in the history growing without bound off the end of the thing.
Any more questions?
If we have time, can I elaborate on how I think the proof works? And, just to make sure we're thinking about the same thing. I believe you're going to create for every block a Merkle tree for its outputs based on its position and whatever the value is in the UTXO, which is the amount of the script TXID.
It really just needs position information. It doesn't need.
The hash needs to.
It needs to commit to.
Oh, it needs to commit to the hash.
The actual UTXO data, right?
Yes.
And then whenever I want to spend something, I give you the output I am spending together with the Merkle path that connects it to the root, which is per block of the block it was created.
It doesn't have to be per block. I kind of like making it per block because it's a good idea for nodes to store like the top bunch of layers of a true Merkle root, and that's kind of a good spot to stop at.
But we already have a linear amount of data in the blocks that are available. Adding 32x to that isn't that much of a big deal. I agree.
Yeah.
Any more questions? All right. Well, thank you for your awesome talk, Bram.